Greetings everyone. Welcome back into Calc 1. We're in the last lecture here. That doesn't mean this is where calculus ends. I hope every single one of you will stick around for my next series of Calculus 2 and beyond. There's always Calc 3, Advanced Calculus, Differential Equations, all of them very much as interesting as this one. For the one last application, something that will carry on into the next several calculus courses, a couple of things that use integration. First one is the length of a curve. Sometimes it's called arc length, but also arcs are kind of like pieces of circles. Curve length is a more apt description for this one. Okay, and it boils down to a calculus version of Pythagorean theorem, really. So look, if you've got some curve, f of x, okay? If you zoom in on one little piece of it where I've picked 2 points, the difference in the x's is delta x, the difference in the y's is delta y. And if you zoom in on that piece of the curve, the 2 points that I've picked, if the delta x is how much the x's change in between the two, the delta y is how much the y's change. And according to Pythagorean theorem, if I label this delta s, in other words, how much on average the position of the curve has changed, or sort of like a weird approximation of the length of a curve. Of course, delta s is not exactly the length of this piece of the function, but the only reason you can see the difference is because we've zoomed in. Okay. Beyond that, we're going to be taking a limit as the delta x goes to 0, right? So that's where the calculus is going to jump in. But notice the delta s has a Pythagorean relationship with delta x and delta y, because it basically makes a right triangle between all of the changes there. So if I take the limit as delta x goes to 0, then of course also delta y is going to go to 0, and so is delta s. Now that doesn't mean we're actually going to get to 0. Remember, that's the whole point of the limit. Okay, if we take that limit, what we're actually going to start talking about are the differential pieces, right? The things that have the width of a point, an infinitesimal amount. Delta x going to 0 becomes dx, which causes delta y to become dy, which causes delta s to become ds. And yes, this is sort of a hand waving. It's not an actual full-on proof, but you should be getting the idea here. I'm taking it to the extremity of smallness, just like a derivative would with a slope. But instead, I'm talking about the individual pieces. But speaking of derivative, that does actually come into play. ds is equal to the square root of dx squared plus dy squared. That's our Pythagorean identity between the infinitesimal little pieces of change inside of the function. So if I manipulate by multiplying by dx over dx out here, right? It's just multiplying times 1. But I leave the top dx outside and I distribute the bottom dx into the radical. Okay, now it's in the radical. That means they're getting squares. Dx squared over dx squared is going to give me 1. And dy squared over dx squared is going to give me the derivative squared. This is the slope, right? Squared. And then the other dx is still on the outside. So ds is equal to this square root calculation times dx. Therefore, if I integrate all of the little ds's, I'm really integrating that calculation, the square root of 1 plus the derivative squared times dx. So this would then give me the length if I were enumerating some. Hey, let's get all of these ds's, right? Let's grab all of the ds's from here to here. So I'm not adding up dx's. Dx's would be counting along an axis. Dy's would be counting along an axis. I am actually adding up little pieces of curve length. That's what ds represents, little itty bitty pieces of curve. Okay? And I'm adding up a whole bunch of them. And this is actually how you can calculate the individual pieces. So when I integrate this, I'll get the length between 2 endpoints. Here's an example. Let's say I have a linear function y equals 9 minus 3 over 7x. you actually already know how to do the length of this because I'm going to go from the two intercepts here. It intersects the y-axis at 9 and it intersects the x-axis at 21, which means it makes a right triangle with a height of 9 and a width of 21. And since it's a right triangle, it will follow Pythagorean, so the length of the piece between those two will simply follow a progression of Pythagorean reductions here. So you get 3 square root of 58. Now from the calculus end, my function y equals 9 minus 3 over 7x has a derivative of negative 3 over 7. So if I do the integral of the square root of 1 plus negative 3 over 7 quantity squared, right? That's just a number. I can actually take the square root out of the integral in this one because there's no x's in there, which means I would just be integrating dx, which is just x, from 21 or from 0 to 21. So 21 minus 0 times that square root. Simplify the square root, you get 58 over 49. Square root of 49 is 7. 7 into 21 gives me 3. Square root of 58. Not a coincidence that these are the same, okay? This is just the calculus way of getting the length of a curve. The upside to the calculus way is that it does not have to be linear. Pythagorean, of course, it would have to be linear, okay? I'm just showing you an example here. So I want to show you a couple of examples just real quick of how I can just take some function, any function, pick 2 points on the function, and we can find the length of that function. In other words, you'd just be taking that piece of the curve, and if you could straighten it out and measure it, then that'd be what you'd actually have. But we don't have to straighten it. We can just calculate how much length it has being all coiled around whatever path it's following. Let's throw down a couple of quick examples of finding a length of a piece of a function's curve. So I have a function y equals 2x to the 3 halves plus 3, and I want to find the length of that curve when x is allowed to vary from 0 to 9. Okie dokie? So then all I'm going to do is set up my integral. The length of the curve, s, is going to be equal to the integral from 0 to 9, square root of 1 plus the derivative squared. So the derivative of this is going to be 3 halves times 2, which is going to be 3, x to the 1 half, and then that's going to be squared, because the derivative of 3 is 0, I'm not going to include it, dx. So I took the derivative, right? And then I plug it into the formula. So then the length, integral from 0 to 9, let's see, I've got square root of 1 plus 9x times dx. Well, I can't just outright do that one, can I? I'm going to need to use a u substitution. So let's do that. I am going to let u equal 1 plus 9x, which means du is going to have to equal 9 dx. So I need to fix my integral here. I need a 9 times the dx, which means I'll need a 1 over 9 times the outside there. Alrighty. So my 9 dx becomes my du, and my 1 plus 9x becomes my u. And instead of square root, I'm going to write 1/2 power. So I have integral u to the 1/2 du. And now let's talk about what our limits become. When x is 0, u is 1. And when x is 9, 9 times 9 is 81 plus 1, I have 82. And times the 1/9. So then I have 1/9 times 2/3 u to the 3 halves evaluated from 1 to 82. So then that gives me 2 over 27 times 82 to the 3 halves minus 1. And of course, that's as far as you'll want to go by hand. I certainly don't want to try and do 82 to the 3 halves by hand. So 82 to the 3 over 2 minus 1 times 2 over 27. 54.93. Right? Is the length of that curve on that interval. Here's that function. Here's the point at 0. Here's the point at 9. Notice the scale on the y-axis is way off of the scale of the x. That's so it fits on the screen. This is the piece of it that I've highlighted in red. So if I turn off the blue, see, we're doing the length of this piece of that function. And as you can see, it's 54.93 as we calculated. Next, I have the function y equals 1/2 e to the x plus e to the negative x. This one also has a nickname, by the way. This is called the hyperbolic cosine, also called cosh of x. The hyperbolic functions are a very important set of functions that serve a similar purpose to sine and cosine do with angles of circles. The hyperbolic ones do certain angular type of properties and area properties with hyperbolics instead of circular. There's also elliptical versions and things like that. But anyway, so the way this one is defined is what we call hyperbolic cosine, cosh of x. But we'll just go ahead and leave it in its current form since we already know how to do the derivatives and whatnot of that. Okay, so here we go. I'm going to do the length of this curve on that interval. S is equal to the integral from 0 to 2 square root, and then I've got 1 plus, and then I'm going to take the derivative of this and I'm going to square it. Okay, so then I'm going to have 1/2 is still part of the derivative. Okay, so leave that in. That's going to give me a 1/4. The derivative of e to the x is e to the x. The derivative of e to the negative x is negative e to the negative x. And then that whole thing is squared because I'm doing the derivative squared. Dx. Okay. So then from here, let's see what we can get. I have s equals integral from 0 to 2 square root. I've got 1 plus 1/4 times. Now if I square this out, of course I'm going to get e to the 2x. And then I'm going to have e to the x times negative e to the negative x. I want you to realize that when I multiply these two, the exponents add because they're the same base. So I'm essentially getting e to the 0, which is 1, or in this case negative 1, but I'm getting it twice. So negative 2. And then I'm also going to get plus e to the negative 2x dx. All right. So what I'm going to do now is I'm going to rewrite this 1 here as 4 over 4. And the reason I'm going to do that is because I'm actually going to factor out the 1/4 here. Okay? It's in a square root, so when I factor out the 1/4, that's going to give me a 1/2. Okay? Integral from 0 to 2. And underneath my radical, notice that I'm going to have the e to the 2x. I'm also still going to have the e to the negative 2x. And then when I factored out the 1/4, okay, that piece is gone, and this was left to be a 4 minus 2. So I've got plus 2 plus this. Now I'm hoping that you see a pattern here between this and this, because what I've actually got is the exact same setup, just it changed from a minus to a plus, which means it's this exact same type of binomial squared, okay, but with a plus instead of a minus, dx. So I've got 1/2 integral from 0 to 2 square root of e to the x plus e to the negative x, and that whole quantity squared dx. Okay, now of course now I've got a square root and a squared, which, yeah, I know you want to say the big C word. Remember, they do wipe out, but they technically leave behind an absolute value. You've got to be double careful with these. A square root of a square does leave an absolute value. So if this integral were to ever go negative, I would have to split it into multiple pieces. However, we're lucky. Exponentials always give positive values, right? And they're being added, so the whole thing is going to be positive guaranteed. Therefore, I can just do the integral of just this, e to the x plus e to the negative x. So my s is equal to 1/2 of e to the x minus e to the negative x. Notice that the integral, right, brought out that negative again. And I'm evaluating from 0 to 2. Right? Okay. So then when I plug in 2, I've got e squared minus e to the negative 2. And then when I plug in 0, e to the 0 minus e to the 0 is 0. So I've actually just got this right here, which if you've ever seen the patterns before, you'll notice this is very similar to what we started with, except it has a minus. This is actually equal to what we call the hyperbolic sine, sinh, of 2. Let's get a decimal approximation on that guy. E to the 2 minus e to the negative 2 divided by 2. 3.62686. So we'll say about 3.63. 3.63. Right? That's what I was getting from that calculation. But also, if you hit hype and sine, you'll see it'll give you the sinh function, right? Let's see what happens when I plug in 2. The hyperbolic sine of 2 is the 3.63 value that we were getting. So here is this graph. You can see it looks a little bit like a parabola, but that's not it. It's actually what we call the hyperbolic cosine function. So if I turn this off and this on, you'll see they actually are the same shape. Alrighty, we're interested in between this point and this point, so just this little bitty piece here should be the only piece that's on. So if I turn this off, you'll see this is all we're really doing the length of right here. The length of this piece, which we calculated already to be the 3.63. That piece right there. So one last application of integration here is going to be back to solids of revolution, but instead of the volume inside of the solid, we just want to calculate the surface area, the amount of surface that is formed when you take a curve and revolve it around something. Okay, so the idea is simple here. It's just like the volume when we were taking slices and discs. So if I can slice discs and add up all of the areas, right, then if I want the surface area of something, when I take a slice, I would just want the circumference of the disc slice. And if I add up all of those circumferences, it would make up the entire outer surface, right? So the circumference of the circle is 2 pi r, but remember you got to do times the thickness, right? Which technically is going to be ds, because we're following the edge of a curve. We're not just counting along an axis anymore, okay? It's not the slice thickness going along the curve. The things are going to keep changing along the length of the actual curve. So as we just saw a moment ago, ds, the actual calculation, is the square root with the derivative. So then to get the surface area of something that's being revolved, I simply need to set up some sort of radius function in terms of x. A lot of times when you're doing it around the y-axis, your radius will be x itself. And if you're doing it around the x-axis, it'll be the function itself, okay? But regardless, after you set up that function, you have your ds length calculation, and then you simply have an integral to perform, okay? Let's get a couple of examples of this formula. So let's get a couple of examples of doing a surface area of revolution to wrap up the whole semester, right? So I have a function, f of x equals 2 square root of x. I'm interested in the interval from 4 to 9 on the x-axis, and I want to revolve this curve around the x-axis. So I have 2 square root of x here, and I'm interested in the interval from 4 to 9 here, which is this piece of the curve here. And I want to take that piece of the curve and I'm going to revolve it around the x-axis here, right? So it's going to be something like that. And we're going to be getting the surface area of this thing that happens here, basically. We're just going to be getting the surface area around this ring, if you will, in the front and the back, right, all the way around. We're interested in the interval from x equals 4 to x equals 9, which means I'm only interested in this little piece. And we're rotating it around the x-axis here. So it's going to start doing something like this, which you'll be able to see it better if I do it this way, all the way around. So we're calculating the area of this surface that is formed by rotating just this little piece around the x-axis like this. And it's going to make this ring-shaped surface. So let's start with finding the derivative here. Of course, f of x is equal to 2x to the 1/2. So f prime is just x to the negative 1/2, right? That's my derivative. So I'm going to set up my integral here for surface area. I have 2 pi times the integral from 4 to 9. Now I need a radius function. Well, remember the radius function is going to be along the slice, right? And I'm slicing this way. Notice that the radius is actually just my y value, or in other words, the function itself. So my radius function is 2 square root of x times the square root of 1 plus the derivative That's going to be 1 over x to the 1/2 squared dx. All right, so now that we've got it all set up, I'm going to manipulate some stuff. I can bring my 2 out front here, and that's going to give me a 4 pi integral from 4 to 9. I've got a square root of x, and right here in my square root, I've got a 1 plus 1 over x, right? Because the square and the square root there basically are going to be opposites. And I would say worry about an absolute value because of the square and square root, but we're going from 4 to 9 of x, so it's all positive anyway. Don't forget, 1 is the same thing as x over x. So really what I can do is I can merge these into an x plus 1 over x, like that. The reason why that's good is because I can rewrite this inside of my integral here as the square root of x times square root of x plus 1 over square root of x, which is going to allow me to take away those 2 square roots there. So then my integral ends up being 2 pi integral from 4 to 9 square root of x plus 1 dx, which I can do with a quick substitution, right? My substitution would be to let u equal the inside, the x plus 1. So du would actually be just equal to dx, because derivative of x is 1. Okay, so then my integral would become, oh, I don't know why I said 2 pi here. This should be 4 pi. Integral from 5 to 10, right? Because u is x plus 1. And then I'm going to have u to the 1/2 du, because dx is now du, x plus 1 is u, square root is 1/2 power. That's going to give me 4 pi times 2/3 times u to the 3/2 evaluated from 5 to 10. And I can just finish that up. 4 pi times 2/3 is 8 pi over 3 times 10 to the 3/2 minus 5 to the 3/2. And I really, there's nothing much else. You could maybe factor a 5 to the 3/2 out, but it's not really going to do you any good. It's really just best to leave that kind of like it is. One more example. I want to take the function g of x equals 9 minus x squared, right? Downward facing parabola, on the interval from 0 to 3, which happens to be y intersection to x intersection there. And I want to revolve it around the y-axis, right? So basically, I'm going to get the cup shape, right? A downward facing cup shape like this. But I'm really just getting the surface area of this thing, right? I'm getting the surface area of it's kind of like a thimble shape, right? Like a little thimble bell or whatever that you'd fit on your finger, or maybe if you want an actual bell, right, shape. Basically, I'm going to be getting that. Here's our curve, and we're rotating this one around the y-axis here. You can see it's our curve 9 minus x squared. I'm interested in the piece of it from here to here, right? And I'm going to rotate that around the y-axis. So we're finding the surface area of this thing that's been revolved around, this surface that has been formed by doing that revolution. Now, of course, if I'm revolving it around the y-axis, my radius is just going to be the distance from the curve to the y-axis, right? That's going to be the radius from here to here, which is just x. So let's set up our area integral here. I'm going to have 2 pi integral from 0 to 3. X is my radius. Square root of 1 plus, what's the derivative here? Negative 2x, right? Squared times dx. So then my surface area then becomes 2 pi integral 0 to 3 x square root 1 plus 4x squared times dx, which again, I need to do a substitution in order to follow through. Luckily, I can already see that we're going to succeed because I need something with a derivative of an x squared, which means I'm going to need an x, and we've got that ready to go. So if I let my u equal 1 plus 4x squared, then du is going to be 8x dx. So in other words, I need an 8 here, right? In order to do my substitution, I need to fix this with an 8, which means I'll also need to divide by an 8. And then I can rewrite this in terms of u. So 2 pi over 8 reduces to pi over 4, right? That's this. Integral, when x is 0, u is 1. And when x is 3, 4 times 9 is 36, plus 1 is 37. And then I have u to the 1/2 du. Because my du is the 8x dx. And then I have the u taking the place of this. Square root is the 1/2 power. Alrighty. So then I've got pi over 4 times 2 over 3. U to the 3/2 from 1 to 37. So if I reduce this here, I'll have pi over 6 times 37 to the 3/2 power minus 1. Whatever that may be, right? Because I certainly don't want to do the square root of 37 to the 3rd power by hand. All right, so I hope that this has helped you finish up in understanding how we can use integrals to add up layers of things, surface areas, and also arc length in the beginning of this lecture is something that will come up quite a bit. And I hope to see you all in Calc 2.